like to introduce Professor Carl Williams to you. He is an adjunct professor in the Department of Physics at the University of Maryland, College Park, USA. He obtained his PhD from University of Chicago in 1987. He has served several leading institutions, including University of Notre Dame, University of Chicago, and NIST, Atomic Physics Division. He is the chief of the Atomic Physics Division and fellow of the Joint Quantum Institute between NIST and University of Maryland. He has won numerous awards and fellowships. He became a fellow of the American Physical Society in 2002 and received the Silver Medal for Leadership, Department of Commerce in 2003, and Arthur Fleming Award for the Scientific Achievement in 2006. His current areas of research of interest are high-speed quantum key distribution, security of quantum communication, physics of the neutral atoms in optical lattices, and quantum computing with neutral atoms, quantum computing architectures, many-body physics associated with Bose-Hubbard Hamiltonian. Up to Professor Carl J. Williams, please.
Thank you very much. I'd like to thank the organizers for inviting me. It's been great being able to come to India and have the pleasure of giving this talk. What I really want to do, and so I will skip through some of the slides here, I really want to kind of give you an overview about one of the approaches to trying to build a quantum computer. And one of those approaches is based on using neutral atoms. There are a number of approaches underway at NIST, but neutral atoms is the one I'm going to talk about. And again, this is really about an overview of what's been done in the last 10 years. And I hope when we get toward the end that you walk away with the view that this is an extraordinarily hard endeavor, and yet we think it's possible. We think it will eventually be done. But it is non-trivial, and there are a lot of issues to overcome. Again, I can say a few words about NIST. Most of you, National Institute of Standards and Technology, those of you from India have the National Physics Laboratory India, that is our sister institution. That is NIST and NPL India are basically just our government's different arms for doing basic standards for all commerce. So with that, I will start. And so what I'm going to do is my outline is basically I'm going to start with a little kind of an overview of how I look at quantum information, then talk about how one would try to do this with neutral atoms, how we go about it, and then start actually talking about some of the specifics and examples of experiments and things that have been done and where we are with doing this with using what we call optical lattices, and I'll explain what those are, and quantum computing. Talk about some of the problems that come out of trying to do this. And again, if you heard this morning's talk, if you want to talk about being cold, the atoms that we typically deal with, we need to be at temperature scales that are in the picokelvin above absolute zero. And yet we do this routinely these days. We have the technology, the means to play with them. These are some of the best understood quantum systems in the world, and we can control them, and I will show you some of the kind of things onto that. But part of doing this is also coming up to with how do I build the architecture for a whole new kind of computer? And that will come in, and then I will kind of speculate toward the end about where things are really going with the neutral atom systems. So let's start with what is quantum information. I like this quote because I think this quote is not wrong. There's a lot of things that are said about quantum information that kind of aren't quite correct. And this one, because it has a little less content, is perhaps a little better. It says, quantum information is a radical departure in information technology, more fundamentally different from current technology than the digital computer is from the atoms. It is really a whole new paradigm shift. I think this is a great thing. This is, again, by Bill Phillips, one of NIST Nobel Prize winners in physics. I like it. I think another way of looking at quantum information is that quantum information actually provides us an opportunity to take advantage of two great discoveries of the 20th century. And one of those discoveries is quantum mechanics. Quantum mechanics is everywhere. I mean, we do not have modern technology. Transistors do not exist without quantum mechanics. It's the semi-classical properties of quantum mechanics that we largely exploited in the 20th century. But we build all of our technology, LCD screens, everything else, are based upon the quantizations and band gap materials and everything else. We've exploited quantum mechanics to build all of modern technology, and yet we process classically. Another great discovery in the 20th century was information science. Now, information, the basic idea of the information content you could have in a stream and all, really comes out as a mathematical field in the mid-20th century. And what's really happened in the last part of the 20th century and now is that we've realized that these two things are not really separate. They're really one and the same things. That information is basically a fundamental physical quantity. That if you can process that information at a quantum level, that requires the coherence, the superposition, and the entanglement that had been mentioned this morning, then you can actually build a computer that would actually be computationally more powerful for a certain class of problems than a classical computer. And that increased computational power could have things to do with how the brain works or other things. And so there's really, this is a remarkable way to go. And I think it really is very, very insightful. I think the first hints of this comes from a famous paper by Richard Feynman. Again, Einstein was one of the great early thinkers of the 20th century. Richard Feynman, I would say, was one of the great physicists of the latter part of the 20th century. And Richard Feynman says this: when we get to the very, very small world, say circuits of 7 atoms, we have lots of new things that would happen that represent completely new opportunities for design. Atoms on a small scale behave like nothing on a large scale, for they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms down there, we are working with different laws, and we can expect to do different things. We can manufacture in different ways. We can use not just circuits, but some system involving the quantized energy levels or the interactions of quantized spins. This is really the first place in literature where you begin to see the idea that one might be able to compute at the quantum level that I know of. And it really is really way ahead of its time. The fact is being out ahead of the things. And he basically said there's plenty of room at the bottom. And what he meant by this is that if we exploit quantum behavior, we should be able to do things we cannot do classically. And again, you've heard some of those kind of concepts this morning, so that's great. I think we are actually witnessing the second quantum revolution, and that you will see people using the weird properties of quantum mechanics to do things that could not be done classically. And surprisingly, it exploits what nature probably has already done. And again, if our brains is found to be truly quantum mechanical, to be a quantum computer, nature has already figured it out. And you know, the reality is nature is remarkable. It often does things, and we are then left to discover its laws. So here is an after-dinner speech, again, by Richard Feynman, now some 20 years later. But here is where he first talks about quantum computing specifically. And if you want to make a simulation of nature, you better make it quantum mechanically. And by golly, it's a wonderful problem because it doesn't look so easy. Now, why would he speculate this? What he knew at this point was that one thing that a classical computer cannot solve efficiently is quantum problems. And yet, if you could do things quantum mechanically, a quantum mechanical device should be able to efficiently solve quantum problems. And in fact, you can see some experiments on this, on just that now exist with optical quantum computers that basically have just produced the Bohr levels of the hydrogen molecule just by a quantum process. Actually, a few-bit processor, and it's quite remarkable that it can do it and everything else. So there are at least some problems that we know this quantum computer can efficiently solve. Not probably all quantum problems, but at least some of them. We also know that a quantum computer, if it exists, could break all present-day public key encryption systems. Public key encryption is essential to us. We go to HTTPS websites. We are effectively using RSA all the time to basically pass information, to put your credit card into that computer over there so you can buy something, other things. Quantum encryption can defeat any computational attack. Now, of course, what's required here is that quantum encryption be implemented absolutely physically correctly. And all the details in doing quantum encryption is really about the physical implementation. It's not about the theoretical constructs. No devices are perfect, and lack of perfection of those devices give ways to cheat things again. But there are other things going on in the sensors realms. Again, one of the most accurate clocks that NIST currently has basically uses quantum logic to actually do its readout. That clock is accurate to 2 parts in 10 to the 17th, or about 1 second in 100 billion years. And it basically is using entanglement to effectively read out the clock. So, and then we can speculate about the other things. I think probably the most advanced effort, if you will look, is that of Dave Wineland or Rainer Blott doing Untitled Chapter quantum computing. They can currently control about 8 to 10 qubits very accurately. They've done a lot of simulations, but remember, we're only talking about 10 qubits. It's not very large. And there's a lot of requirements in going forward. And I will come back to the basic requirements that you have to do to build a quantum computer in a few minutes. But basically, a lot of the key pieces that would be necessary to build a much more complicated device have been shown. So let me talk about quantum information with neutral atoms, the requirements, the general ideas, and where we're going with this. So again, I said I'd come back to these criteria. One of the things you have to do if you're going to build a quantum computer is you have to have well-characterized qubits. The same way that you have to have bits in a classical computer. The problem is in a classical computer, your bit is a very unique bit. It's a bit in which it's like light switches, either on or off, 0 or 1. And you know, if I only had to be 0 and 1 quantum mechanically, life would be easy. The problem is with your quantum bits is the spacing between the energy levels, because you do the superposition, has to be very insensitive to any noise. And so that 0 and 1, I not only have to be able to put in a superposition and not have it decohere, but it must be stable. Those energy levels can't be jiggled by the noise around. It's really a hard thing. You have to be able to take all these qubits and put them in this initial fiducial state. That is, you have to initialize your computer. Again, quantum mechanically, that means typically being very, very cold. Like I said, in this area, picokelvin. And you have to be able to do gates, many gates, before an error occurs, the so-called decoherence, the fact that noise affects your quantum computer. You must be able to isolate it. You have to be able to do universal gates, which means 1 and 2 qubit gates, and you have to be able to read out your situations. And unfortunately, there's also the need to communicate, networking. Most of what you do in a classical computer is move information. You move it from hard disk to cache, from cache to memory, you process it, you throw it up on the screen as a picture. But what you've done is you've moved and transformed that information half a dozen times. And if I'm going to build a quantum computer, I have to be able to do all those things. And those add additional complexities. So this is basically hidden within these are the needs to do things in parallel, to do error correction. And all this is essential to make it scalable. So another way of looking at those that come from more of a computer background is I have to have my quantum microarchitecture. It has to have registers and control in it. I need to have memory. I need to be able to do I/O. This is just my quantum system architecture. I need a classical system to control it. Believe me, this will be the most complicated classical computing system, control system ever built in the world when this is done. It will be more complicated than the Boeing airplane. It's going to control this. And I need a bunch of language and other things. This is not going to be done tomorrow. I mean, this is a long-haul project. And part of the fun of it is really actually thinking about what we can learn about quantum information. So I'm going to talk about how we go forward on pieces of this. But you saw some of the more broad thinking ideas that were coming out of quantum information science this morning. And those themselves are really where some of the benefits are. So like I said, whole pieces of this don't exist. And we're a long ways from piecing all the pieces together. So let's talk about neutral atoms. Neutral atoms basically are ideal for doing quantum computing in some ways. Why? They are the basis of the one thing where we use the strange property, or at least the superposition property of quantum mechanics in the 20th century. The best clocks we have in the world are atomic clocks. NIST, we build these, and we keep building them better and better and better. They're very well understood. We can Rabi flop them, and this is basically just a thing that I can put in a superposition, and it would just oscillate in time. And this is what a ticking of a clock is. And if those levels are very steady, that clock ticks very well. If you disturb those levels every bit, it ticks a little faster, a little slower, and your clock isn't as good. The magnetic levels of the hyperfine states of cesium defined the second by international convention. We realize those things very well. We can isolate them. We know how to do that. And again, this is technology we've been working on for a long time. You need to do state preparation. State preparation basically involves optical pumping of atoms. This is the things that are behind laser cooling and BEC in 1997 Nobel Prize, which Bill Phillips got, and the prize by Eric Cornell, Wolfgang Ketterle in 2001. So again, this is known technology. It's not old technology now, because now we're talking about technology that is just now 15, 20 years old. In fact, laser cooling goes back to the late 80s, and this is where all this begins. But we understand how to do laser cooling. So what's shown here on this lower thing is if I trap an atom in some kind of an external trap, these are typically optical and magnetic traps. I have energy levels. I can bring in two beams slightly tuned from each other, and I can play with the motional levels of the things. And what's shown up in the upper right-hand corner are the magnetic sublevels of those atoms that can be used, and I can pull two of those to be my qubits. You need to be able to detect your state and be able to detect one and only one. And again, because of these magnetic sublevels and selection rules, it is very possible to make one of these scatter light and the other not. So again, this can be done very, very accurately. The universal gates, again, some of these have been demonstrated. The 1-qubit gates, the fidelity is now greater than 4 nines. 2-qubit gates is still not very good in the neutral atom case, but they're being worked on. So what's the general idea of approach? The approach that's been taken at NIST and in a number of other places around the world is, okay, we just start with a bunch of hot cesium atoms that come out of a vapor oven. We laser cool them. We slow them down from room temperature to 100 microkelvin. We then do some little other tricks to do Bose-Einstein condensation of this. There again is a nice Indian in there. Bose, of course, was the first to come up with this many years ago. And effectively, it took only about 80 years for this to actually be achieved. But we finally condensed a bunch of atoms into the quantum ground state, which time there are current atom temperatures on the order of a few tens of nanokelvin. And we can do a little better than that. The next thing they do is they load these into an optical lattice, and that's demonstrated here, and I will say a little more about what an optical lattice is in the next couple of slides. And then you have to start doing the gates, and I'm going to show you how some of this is done. A lot of this is the work of the group at NIST, really led anymore by Craig Porto, but it includes Bill Phillips, Spillman, Steve Ralston, and a bunch of postdocs and all who've contributed to some of the experiments I would talk about, and I would talk about some of the theory work as we go along. So let me talk about optical light forces. There's two ways of looking at light on an atom that is non-resonant to an atomic transition. One of these is to say that the atom is polarizable, and I'm just playing with this polarizability. The other is to go into what is called a dress states picture. And as long as I'm detuned from resonance, I can effectively get a light shift. That is, this second-order interaction will create an optical potential. And so the way I do this typically is with these atoms is there's two pieces to it. A scalar piece that is really related just to the intensity of the light field, and that is effectively the light field polarizing the atom. And you can see this basically as it virtually absorbing and emitting a photon, which will shift its energy levels if it's tuned to the red of an atomic transition. And again, I mentioned that these atoms have magnetic substructure, and that means that they are also sensitive to the polarization of the light, and that means that there are an effective magnetic field potential to these as well, and we'll come back to that because it's essential in how we control and manipulate them. The point is if I take two standing waves, I take a laser and I just bounce it off from a mirror and get a standing wave, I get a cosine squared pattern of this field, and that means a cosine squared pattern in intensity distributions. And if I'm ready tuned, I will go to where the field is largest. And therefore it creates basically an egg-shaped carton pattern in space. I can do this in 2 dimensions. I can do it in 3 dimensions. It's easy. Why those traps are very weak, if I have my atoms cold enough, they actually act as a means for trapping the atoms. Notice these atoms are forming a crystalline structure in light. They're not bonds. They're 500 nanometers apart from each other, 250 to 500 nanometers apart from each other. We can stretch them out. But the fact is with light, I can create any pattern I want. And the reason that you know I can create any pattern I want is all of you have seen a hologram. And a hologram is nothing but a spatial light pattern. I can create that pattern, and therefore I can create that pattern and trap my atoms in it. I've shown you a few examples of the kind of patterns that can be done with just a few beams up here on the table. And each of those spots then can become a place where I can trap an atom if I have the atom cold enough. Better yet, not only can I have this periodic pattern, I can bring in a focus beam, a so-called tweezer, which is now being used to manipulate DNA and other things, and push one of them ever so slightly so I can make it more resonant than another one. And all these tubes basically are going to give me the means to do everything else I'm going to show you. And I haven't gone through all the details of this, but effectively by combining lattices and tweezers, I basically have the means to do arbitrary addressing and to engage in moving and manipulating these atoms. And I will show you results as we come along. I'll just skip this one for a moment. Let me come back to one other little concept that comes in a value. And this has to do with, again, the standing wave light in basically in 2Ds using a pattern that's shown up on the top. And the reason I'm going to show you this is if I have the light polarized out of the plane and you bounce that around, then the polarization where the beams intersect up there, is all polarized out of the plane, and those beams will mutually interfere, all 4 of them, and I will get this pattern here. If I polarize in the plane, again, my light's propagating that way, when it goes across this way, on this path, it's polarized this way. When it comes across this path, the cross-polarize, and I get this pattern. Now, this is just a square with lambda over 2, square root of lambda over 2 this way, or lambda across this way. But together, they give me this double-well lattice potential. And all I have to have is something to change my polarization of my light, and I can manipulate that double-well pattern. I can convert it into a single lattice site or 2. That means I can bring 2 atoms that are in adjacent lattice sites together, let them interact, and pull them back apart. All with just a polarization trick. That is the last little trick we need, because those are all the components I'm going to use to actually manipulate my atoms along with laser beams. So what happens if you take a BEC, a Bose condensate, cool it to near absolute 0, and you down all laser beams underneath? Well, again, anybody who understands Bose statistics understand that bosons are all identical particles. I have 100 Charlies all sitting in my bucket. All Charlies look the same, and I can't tell you which one is which. Now, through the magic of some physics, I turn this lattice up underneath, and a remarkable thing takes place. And I'm going to show you what the data is telling you in a minute. But the thing that takes place is something that you don't read about in textbooks. It's a quantum phase transition in which, at some point, the atoms become unique. They become unique and labeled by their location. Because I'm going to go through a phase transition that will ensure that there is one and only one atom per well site. Now, I don't know which Charlie ended up there, but that's Charlie 1, that's Charlie 2, that's Charlie 3, that's Charlie 4. I can start labeling them because I can label them by their location. This is remarkable because I've made all these individual atoms unique and labeled by location. The way you can see this is that if I have the atoms and there's no lattice on whatsoever, You basically drop it. All you see is what looks like a condensate. It has a single momentum distribution. What you're looking here is basically the momentum distribution of the atoms. But if I drop a coherent particle through a grating, which is what my lattice is, and I have the lattice on, you will see Bragg scattering or diffraction. This is basically what you see off of a crystal of matter. This is the atoms diffracting off of that light field. Lattice gets deeper, you see more higher order diffraction patterns, and all of a sudden it goes away. Why does it go away? Well, in order to get that interference pattern, I have to have phase coherence between my particles and my different well sites. They have to share a common phase. This inside a phase transition basically removes that phase. It doesn't remove any of the correlations in all the correlations in there, but it makes them unique and labeled by location. And so at the deepest lattice site, I fill the first Brillouin zone or the first scattering zone, if you know any solid-state physics. And this is the first evidence that this was being done. So here is slightly later data from 5 years later by the NIST group doing this in 2D. Again, you can see the high-quality patterns that come out of this. Here's a case where the atoms are basically distributed among the whole lattice, and then up there where they have gotten to where there's one and only one per lattice site. So with that and the double well lattice, which, as I said before, basically has this thing that depends upon the magnetic sublevel structure, I can actually control my atoms in opposite well sites. I can bring them together and actually do a gate. So let me show you how that works. So here is, and the movie didn't load, but basically I can distort this into this and back. And that means that if I start with my atoms one in here and here, I can bring them together, and then I can separate them back out. And I'm going to show you the exact protocols by which we do this and some of the data that comes from it. Basically, what I'm going to do is I'm going to fix it to where this well structure is slightly asymmetric, so I can take every one that's in the higher level, that's every other one, A, B, A, B, A, B, and turn all the ones that are in the B sites into a different quantum state. Put them in a different hyperspine state, a different one of the states I would use for the clock. So I now have all my atoms being either in the ground state or the 1 state, 0, 1, 0, 1, 0, 1, all the way across the lattice. Then I distort this in such a way that the red atoms come into the higher level, and the blue in the ground level, but those aren't the eigenstates of the system. The eigenstates of the system are superposition of the red and blue being in the two places. And so they begin to interact and engage. This is my 2-qubit gate. If I do that at just the right amount of time, I end up with the square root of swap, which is a universal gate. And basically I can run a gate. So I'm going to show you the data on this. I need to show you one more thing to show you how the data works again. But effectively it involves just 2 states brought together and then separated back out. All again done using. So the next thing I need to show you is if all my atoms were in blue states, were all in the ground state of these individual well sites, and I dropped them down, what I expect when I look is I see the square blob again that I just fill in the first Brillouin zone. Okay? If they were all sitting in the second state, there's a node in the wave function. So again, if you know something about band structure, or you know there's a node in the wave function, you drop it, the momentum distribution will show a node. And so you will see this pattern. They're in the second Brillouin zone. So I can tell them if they're the first Brillouin zone, I can tell if they're the second one. One more trick. I put on a slight magnetic field because the 2 states I have my atom, my red and my blue ones, have different magnetic components. I can separate them out spatially. So I can look at the red ones separately from the blue ones. And therefore, I can tell red and blue. They're spatially separated. And now I put this all together. I run the gate. And here comes out the data. And here's what you're seeing on the data. Here you see, this is one of my atoms. This is the MF equal -1 state. This is one level of my qubit. This is the corresponding other one. And you will see that when the red one is in the upper state, the blue one is in the lower state, no node. When the red one is in the lower state, as in here, the blue one out here. There's the oscillations. That's the 2-qubit gate. Now, the truth is, when this was done, this was a pretty lousy gate, primarily because, and this experiment was done about 3 or 4 years ago, primarily because I told you we had this perfect lattice with one atom everywhere. Well, they weren't quite cold enough. They actually had almost half of the holes vacant. Half the sites were holes because they weren't cold enough. We had understood that we weren't getting cold enough. We had understood quite a bit from the early experiments, and a lot of work to go on. And so I'm going to come back in a few minutes to show you how much better things have gotten in the last 3 or 4 years, because now this contrast would actually go almost all the way up to 1, instead of being sitting at 0.6 up there. And so things have come quite a ways in the last few years. But this is the first demonstration of a gate. The neutral atoms, they're excellent qubits. We've been manipulating them for 50 years. We know how to do this. Optical traps, we have more and more control of these atoms every day. The double well lattice allows us control manipulation. And we have shown 1 and 2 qubit gates. Now, what I haven't really talked about was this initial registration, this mod-insulator transition that actually comes in. And so I'm going to come back and ask, how well did we do this? Because I just told you it was the problem with having half of the holes in our computer. And so I'm going to show you what the issues are there, what the effects of finite temperatures are, and I'm going to talk a little bit about architectures. So let's go on to the optical lattices in quantum computing. So again, this idea of the mod-insulator transition, again, something that was well known from the 1950s, but was first pointed out in the case of optical lattices. Lattices was done by Peter Cellular in 1998, and again, realized then in 2002. So again, the concept comes out 4 years later, the experiment's done, continually being refined. We've done a fair amount of work on trying to understand the whole things and the roles of finite temperature in those lattices. And so I'm going to come back and try to talk about those. So I showed you the data, and as I said, why everybody agreed that this was great evidence for this mod-insulator phase transition, I told you there was exactly 1 per hole. Well, if it had been done perfectly, there would have been exactly 1 particle per well site. I told you a minute ago that over half of more holes, because it wasn't good enough. So let me come back to the Hamiltonian for the Bose-Hubbard model and some physics. And I want to talk about it because if you go and read the literature here, and I will give you some references on a few things. One, you will see this thing written in second quantization form. Sometimes you will see a J here, sometimes you will see a little T here. I will use mostly the little T. I started this slide with J. The reason is all the atomic physicists like J. All the condensed matter physicists use T. We're 2 physics colleagues who were separated by a common language. But effectively, this is the hopping term. This is a term that basically takes a particle at site B and destroys it and recreates it at particle A. It's the tunneling of a hopping from one well site to the next. The other term is this term with U. And this is an on-site term because it basically involves 2 of these annihilation and 2 of these creation operators. But it basically measures how many particles I have at the site. And I have to pay a pairing cost if I put a second atom there because the atom-atom interactions will shift the energy level. When this term dominates, when J dominates, or the tunneling or the hopping term dominates, then I basically get a superfluid. The atoms are distributed everywhere. If I basically make this term much smaller, which I can by raising the lattice, and make this bigger, I will go through this phase transition. So again, those of you who know basically solid-state physics band structure, when I have the superfluid, that is when I'm dominated by the kinetic energy of the hopping term, I basically have all the particles at the bottom of the Brillouin band. If I drop it, I would see this nice single spot. If I go to the other regime, where I have made U much bigger than T by raising the lattice, and I end up being commensurate, and this is again an issue, I have to have, if I had a very uniform lattice, I would have to have exactly as many particles as I had lattice sites, which looks to be very difficult. I would end up with 1 particle everywhere. And the excitations would be gapped because I would have to pay the cost U to cause a particle to hop where another particle already existed. If I was incommensurate, I would get 1 particle everywhere with all the others then forming a superfluid above it. That's a problem But it basically describes the general physics, and I'm going to tell you how you avoid this latter problem in just 1 second, because it's another one of those details. Let's just talk about how large this problem is, because I tell you, the quantum computer we have, the little simulator we have, can emulate this problem perfectly. And if you wanted to go take one of these example configurations, and you'd like to diagonalize this problem exactly for 12 wells, 12 particles, you only have to diagonalize a 1.3 million size matrix. That's for two-level systems. So you can imagine if it was 100 particles and 100 wells, how big that Hamiltonian already is, the space. Notice the system in the laboratory always finds the right answer. Quite robust. You can say I'm simulating the Bose-Hubbard Hamiltonian by simulating a natural Hamiltonian. But I want to point that out. So again, here's an example configuration. What I have is this second quantization Hamiltonian again. Here's the hopping term, here's the pairing term, and I've added another term, and I'm going to show you what that term is in one moment. Here's an example configuration. Here's the same configuration. Well, let me back up one. So here it is an example configuration, but I told you if I had two particles here, they are slightly higher energy. Let's see if I can go forward. Here, I just shift those up by an amount u. And the last thing that I want to do is I want to take and add an external trap on it. And that external trap is key because it will always ensure that I'm commensurate and allows me to do everything that works in the lab. So there is a presence of an overall harmonic trap, which is this last term in the Hamiltonian right here. So that's really what a cross-section along 1D of the trap is. In experiments at NIST, we typically have 50 to 60 web sites across one direction. So if we do this in 2D, we are talking about 3,600 atoms. 3D, we're talking about on the order of 100,000. So we can do in 1, 2, 3D. It's no big deal. It's just lasers again. So let me show you exactly how this mod insulator works. And again, this is a nice little physics. You know, you go in, you put your first particle in. The lowest energy is clearly in the center of the trap. The next two particles will go into the adjacent ones because slight increased energy do that harmonic. Next atoms will go in until I get to an energy of roughly U. At roughly U, I can either go here or I can pair in the center. So the next particle goes in, pairs in the center, and goes to the edges. And I can just keep adding particles more. And so, again, depending on my total chemical potential, I can control how many atoms I have. And I have control knobs for doing that. I can ensure it's 1, I can ensure it's 2. I can actually build this structure. The interesting thing about the neutral atoms is there's no adjustable parameters. All these parameters are basically determined and known from the atoms. We can go calculate any number that goes into this model. If the theory and the experiment don't agree, it's because we don't understand something. So this is, again, one of the benefits about doing this with neutral atoms is we can calculate everything. We have all the means. We can tell you what the tunneling term is, what the pairing term is, what this little A term in there is the scattering length. It has to do with the interactions between the atoms, which we can actually calculate from first principles as well. We've been doing this for years. We know all these things, so we understand the whole problem. We understand this complete problem very well. And I'm going to skip those, and I'm going to come back to another work. And this is work of a student of mine who's now graduated and now working for Intel at the microfabrication facility out in Oregon. Kaushik Mitra, of course, is an Indian student. Came from India, worked with me for 5 years, and I'm going to talk about some of the work he did with me while he was there, because it's really on looking at understanding the mod insulating problem and the effect of finite temperature. We spent a fair amount of time doing this. Again, one can look at the phase diagram of these things, and at t equals 0, you basically have a situation where you have a phase diagram that I can fill up with 1 particle, 2 particles, 3, and if I have a harmonic trap, I will get a layered structure in there. In fact, if you set the tunneling term to 0, that term on the right is basically diagonal, and anybody in this room can solve that problem. So basically, this is what that phase diagram looks like. I'm going to come back over and tell you a little bit more why we're looking at it. Again, the state I want is 1 particle everywhere. I want the state 1 particle, and this is what this label is meaning. It's 1 particle in site 1, 1 particle in site 2, site 3, site 4, one in each lattice side. That's the state I want. Well, if this tunneling term is strictly 0, I get this target state. But it's never going to be strictly 0 because there's never anything such as a perfect system. There's always this remaining quantum noise. And that quantum noise basically takes a particle from one side to the next side and basically creates these 0-2 holes. The reason I tell you that is because I told you we had problems with the initial experiment. And I'm going to hint at that a lot of the problems had to do with this term and one other term in the problem. And in order to get cold enough, I have to be cold relative to T upon U. And this is where I said you need to be in the picokelvin. Because when we look at that, we effectively have to be down around picokelvin to make all this work out. So again, one can write this down and one can go do the modeling of it. I would say if you go to a finite T, like I said, you're always there. There's always a little pieces of superfluid as you go across this harmonic trap. And I'm going to show you a case in a minute. This is one where at the center there's basically 3 particles because I've drawn the chemical potential up to 2.5. So at the center of the trap there's 3. Then there's a superfluid ring. There's a plateau with 2 and 1. But I'm going to show you pictures of this as we go out. Here is actually Numerical Simulations from 1998 by Peter Zoller. And again, at that point, everything was being done numerically because nobody could actually do these problems analytically. This was all the work that Kaushik did that we can now have analytical solutions to all this stuff. It took a few years to figure that all out. But effectively, here you see a situation where they have a chemical potential of about 1.7. They have a plateau of 2s in the middle. Then they have some superfluid, plateau of 1, and some superfluid again. And I'll back up again. This is the case where they have a chemical potential out here. You basically saw middle 2. You come over, you see some superfluid. Come over onto another ring that was 1, and you see some more superfluid at the edge. That's what those demonstrate. And basically, I'm going to go through this very quickly. Kaushik showed how to do all this analytically. And that was very crucial because it gave us the tools to do a number of other things and to begin to understand all the problems. So I'm just going to say Kaushik solved this problem. Great. He was a great student. Moreover, not only did we understand the regions where there are 3 particles, but we understand these superfluid regions. We could basically describe the quantum states in those regions as well, and all the excitations in there. And he worked through all that. It's a wonderful thesis. Again, I told you about this. By having this harmonic trap, I actually have the ability to have both the commensurate and incommensurate regions there. This would be what would happen if you basically had no interactions. U was 0, and T was also 0. If you put in interactions, you open up these gaps where the superfluid exists, and you also get these gap spectrum here, which is just the cost of paying a pairing energy in the different rings. Again, that's just the model of the stuff, and this is really the work that Kaushik did, which is quite remarkable. So last thing is I'll show you one more thing. Again, if you do this in 3D, this superfluid ring is really a shell superfluid. And for those of you who know something about 2D superfluids, you know that there's Koster-Lattices transitions in them, or you get the formations of vortex-anti-vortex pairs. So one of the comforting things out of this was, when we were done with this, we started looking at this and we said, oh, golly gee, if the people go back and actually recreate an image of their 2D clouds where the superfluid is, they should see BKT physics. It hasn't been done yet, but there are a number of people working at trying to see that. Again, it will be a confirmation that we understand those systems far better than we did a few years ago. So basically, I'll summarize that section. The Monad state can be used to do massive register initialization, but you really have to be cold. But we also understand that temperature drives the excitations to the edges of the trap, to these superfluid regions. And so what I want to do is I want to show you how far things have progressed since those early experiments. And so I'm going to just touch on a number of experiments now largely coming out of Emmanuel Bloch's group at the Max Planck Institute in Garching. So this is again from a Nature paper just last year in 2010. And basically, this is similar to the initial experiments. Here's where he has a mod insulator where there's only exactly one atom in the middle. And you can see, he can go in and individually see the atoms. You see some other atoms around, a slightly bigger one. Eventually he gets to where he has so many atoms that he's beginning to get 2 in the middle. And you can see the 2s from the 1s, so you can see the superfluid These are actual images of atoms in a lattice. In situ imaging of individual atoms in a lattice in a single plane. Those are absolutely magnificent experiments. Moreover, he can bring this objective in and focus down on one atom, so he can push that one down in energy, make only it resonant, so he can flip one atom while not flipping others. Want to see the pictures? Again, this is a nature picture this year. Here he starts out with his condensate, he goes in and he flips all the atoms into the second quantum state in that B picture. The other atoms are there. He hasn't flipped them. But he can go in and flip the ones he wants. Not only can he flip the ones he wants, he can write whatever he wants in there by flipping just those atoms and writing the pattern. And can he go back and image them? Again, truly remarkable because it's showing single-site addressability as well as ability to create the two states that you need for this quantum computer. And we already know how to do the double well lattice thing. Finally, I mentioned, and we knew this, and again, Manuel Bloch and I had many conversations about the early experiments on the mod insulator stuff because he was involved in the first experiment doing that. And we talked about these two zeros. Imagine I have this particle has popped over here. And remember, I told you this correction for this wave function involved the particle going next door. In reality, quantum mechanics really requires this. The only way I know I can't freely tell the next door is by having, quote, some awareness that the next site is occupied. This virtual process from 0 to 2 is essential to do that. But again, with this imaging, if I come back in, I know how many particles I have, I know what the probability is, and I can go calculate exactly how many pairs I should have due to these virtual processes. So if I take an image, I can see how close I am to truly the t equals 0 things. And in fact, in this paper, if you go read it, they basically have done that. They basically are looking at that mod insulator state, and they are very, very close to getting close to absolute 0. This is really remarkable breakthroughs and everything else, but it shows you just how far the field has come in just the past 3 or 4 years. All those pieces are going to get pieced back together, and that leads to the next thing. How do I actually build this neutral atom architecture? Or so to talk about how I would go and piece together the greater architecture, I need to do this. And then I want to also ask the questions. Is this really about building a general purpose quantum computer, or are there other things you want to do with this? Again, scalable quantum architectures, this is back from 2003, some theory work again that Gavin Brennan did when he was working with me, and Daejeon Sung. Gavin's, again, very brilliant people. One way of looking at it is, you've all seen probably the circuit diagrams for doing quantum gates. Basically, each one of these is a qubit. So this is qubit 1, qubit 2, qubit 3, so forth and so on. I want to do an interaction between qubit 1 and, say, qubit 4, and I want to do a controlled interaction in which I do a Hadamard here, depending on whether this is a 0 or 1. I can write any quantum algorithm out in a set of gate operations like this. If I want to basically measure a qubit, I can basically take another qubit in state 0, I can do a couple knots and measure it, and I can basically determine and do quantum error correction and other things with it. But it requires you to be able not to just interact qubits with this next door, but to interact arbitrary qubits, to wire up your computer the same way that you do in a real digital computer. So for fault-tolerant quantum computing, it is necessary that one can interact arbitrary qubits, and you desire to maximize the parallelism of the quantum gates in order to make this work. If I'm going to scale it and I'm going to make this work, I have to be able to do that. So here's my optical lattice quantum computer. And my problem is, at my next operation, I need to interact atom A and B. But I only have nearest neighbor interactions. I don't have wires. What do I do? Well, I'm going to show you the solution to this problem. It's a nice thing of piecing together a bunch of other people's work, but it is a fairly elegant solution. I'm going to show you actually how you do this. And one way of doing it is just to swap the information all the way over there. That doesn't scale very well. There are other ways. I could put microcavities around this and try to optically connect them. Oh, that's really hard quantum mechanically. People have done this, but it's very, very hard. If you have ions, they have a common mode, and you can actually use the interaction of those ions to do it. And this is, in fact, how they do gates in the ion trap quantum computing arena. But the interaction is always on. They cause noise and decoherence, which is one of the limitations to the ion trap quantum computing as well. So I'm going to show you another solution. So the solution is, I need to do this, but there are no quantum wires. And so I'm going to tell you how you do this. I'm going to tell you I'm going to create a quantum bus for doing this. That is the same way that your computer has a bus. I'm going to create a bus for these. And I'm going to allow these for interacting non-local memory qubits. And here's how I'm going to do it. I'm going to go back to my lattice. And the thing I'm going to do is I'm going to break my lattice into different things. I'm going to break it into little yellow cells, which are my memory qubits, and everything else I'm going to use to create my wires. And you say, how does that solve the problem? Well, I will show you this in a minute, but let me tell you, if I need more communication capacity, I just create bigger roads between my blocks of memory. No problem. It's just a layout problem. Now, let me show you how I'm going to use those roads. Well, again, there is this idea about being able to teleport gates. If adjacent to atom A and B, I have this entangled pair, I can then actually do a set of operations that effectively is equivalent to doing this control U between A and B. But I have to have the entangled pair adjacent to A and B. So trick one is to get that entangled pair adjacent to A and B. And this idea came out in 1999 and 2000. So like I said, I'm going to piece together a number of people's ideas. This was the idea of basically doing non-local gates. The next one is entanglement swapping. So I told you I can bring every other atom together. So simultaneously I bring A1 and B1 together, A2 and B2 together, A3 and B3. I do all those together. Bring them together, I entangle them. Then I come in and I do these Bell measurements across the open links. The result is that the two qubits at the end are now entangled, and those in there are done. Cute. I can do that. I'm creating some more entanglement. So I can repeat this process in many ways, because now I have not only the N ones, but the next N ones done as well. Again, 1993 and 1999. And now I'm going to just marry that into my roadways. And by doing those gates in parallel in a number of operations, I can basically, doing measurements on the inner ones, looking at the parity of my results, I basically can entangle arbitrary things there. So let me give you an example of that. Let's say I'd like to interact A1 and B1. Well, not only do I want to interact A1 and B1 in my next cycle, I also want to do A2 and B2, A3 and B3, A4 and B4. Those are my next gates. What do? Well, I do those one round of entanglement. I then do the Bell state measurements. I then have an entangled pair adjacent to A4 and B4, another one A3 and B3. And I can now teleport my gates. Moreover, you can go in and you can show that even in the presence of noise and errors, that this scales much better than swapping. We went through and did all this. We can tell you what the thresholds are for doing this. This allows you to build your wires inside your computer. Really cute. Again, it's piecing together ideas, but all these ideas have to be pieced together if you're really going to build this bigger device. And all this is coming. Again, you can go through, calculate the fidelity of these pairs as a function of length, and given length errors and everything else. All the numbers are in the paper that I presented earlier on, and I'll skip over it. Let me point out one other thought, because this comes with a paper I did with Peter Zoller again a number of years ago, is not only can I do that, but if I have a second species of atoms that I can move independently, which you can do again, I can do other things. I can address one of them. I can then bring them over onto my memory qubits, or the qubits I want to process on, move them over, do my gates. If I do gates in different ways, in different patterns, I can pull them back out. I can duplicate it, entangle them, having entangled those two rays together, bring them over and teleport a bunch of gates. I can put a little caveat here. I can pull out the information back in here, come over and read out each of those. Again, these are all ideas that you need to figure out how to do all the things you need to do in this computer and to control it. The pieces are being put together. None of this has been shown, but there are a number of papers on it that have actually talked about how you would do it. So with that, I want to basically end up talking about the path forward and everything else. And again, there's a number of papers out on the benefits of optical lattices. I will tell you personally, I do not believe that one will ever build a general purpose quantum computer based on neutral atoms. Why? In part, the individual control is really difficult in systems. Having said that, within the next 2 to 5 years, you will see papers in the literature talking about digital simulations with neutral atom systems. Digital quantum simulations involving thousands of atoms, because we have the control over them. I think ultimately another technology will eventually win the overall game for the ultimate architecture. But the control is here on these systems at the moment. And so let me talk about some of these things. You heard about cellular automata this morning a little bit. Where there's things like spin lattices, well, I can emulate the spin lattice systems. Those are condensed matter Hamiltonians. I can emulate them. In fact, so-called analog simulations are being done. We basically taken neutral atoms and made them act like they're in a magnetic field. Why? Because we can. We can do it. We can force them to implement a Hamiltonian that we write onto the atoms themselves. And if we can do this also digitally, so we should be able to do these spin lattice models. Unlike cellular automata, you can also do quantum cellular automata. There's a fair amount of work on that. And like I said, this is really work of Gavin Brennan and Jamie Williams. But effectively, you can do these quantum cellular automata. I'm going to show you some of the things you can do with that. This is easy. This is a little more difficult. This is very difficult. This is general purpose control. And I have to have that big external computer system controlling this to do that last piece. It's really, really hard in all the error correction. But doing the partitioning for a quantum cellular automata, you basically, unlike the classical automatas, just being 0, 1, you have to have 2 sets of rules. You have to have step 1, step 2 rules to make this work. But if you do that, you can basically begin to create some kind of exotic states again. And the kind of states you can do is swapping of qubits in the optimal time passable, entanglement distribution, n-party, GHZ type states, other kinds of things. And these experiments will get done in the neutral atom system in the next 2 to 5 years. The control is there. So, I've kind of run through. There's a lot of information here. I'm around for the next couple of days. You're curious, come ask me and talk to me. I didn't show you all the literature. I showed you primarily stuff that's coming out of NIST and a few other key pieces that are really the state of the art. I think neutral atom quantum information has come a long way in the past decade. I mean, this is really remarkable. If you would ask me 10 years ago where we would be, I don't think I would have thought we would be here. I think a general purpose neutral atom quantum computer is highly unlikely. But I think the real benefit is that we can already see where we can go solve quantum analog and digital simulations, lattice-based problems that are important even technologically, because again, one of the problems that's not understood is we've never been truly capable of understanding why we can't make high-TC superconductors really work. We're not sure we have the right theory, but nobody can solve that model exactly quantum mechanically. They have to make approximations. We will actually do that problem, will get solved exactly on the quantum analog simulator in the next 5 years. Being able to simulate quantum chromodynamics on a lattice and other things along these lines. So with that, I'd like to say I didn't do hardly any of this. The work was really done by a lot of students and postdocs, and I've had the benefit of it. The students and postdocs in the red over here are ones who really contribute to a lot of what I talked about today. And I think I probably left off Gavin Brennan's name off there. I shouldn't have. It's an oversight. But thank you for your time. I'm happy to take any questions.
Questions?
Yes.
At some point when you showed one of your architectures in a grid network, and said with these neutral atoms that you were able to do
so we'll come back to the neutral
Sure,
atoms.
sure. Anyways, so that you could do single qubit gates with very high fidelity, but not so good for 2-qubit gates, right?
With really high fidelity. So the fidelity of the 1-qubit gates is currently at 0.9998.
Yeah, that's right, that's right.
The fidelity of the qubit gates, again, if you had corrected for the holes, which we knew were there, again, there wasn't a loss of contrast we went across, it would just reduce contrast because of many holes. If you corrected for that, we would have guessed at the time that they did those experiments a fidelity of about 0.91 or 92. That's not good enough. But part of the thing is the noise there at that time was known to be largely due to magnetic field fluctuations. I think within the next year or two, you will see them going back and redoing those experiments, and I expect the numbers will get on the 2-qubit gates up to around 0.98, 0.99, which is still not good enough. But I expect they will get there within the next year or so.
If you also said at some point that you could, when you upload the Bose-Einstein condensate on that thing, that you can, after that you can create nearest neighbor entanglement. Well, once you've done that, can you also do measurements?
Yes.
Well,
so you're asking, can we do the Briegel-Rossendorf?
That's right, that's right. So that's right. So why would you care about the fidelity of 2-qubit gates if you have set up the entire infrastructure for a cluster state quantum computer?
So the problem is now understanding the errors in measurements versus the errors in doing gates.
I guess so.
And the answer is, we weren't. I think Emmanuel Bloch really plans to try to do the Rossendorfer scheme for a couple of things to do that. Purely measurement-based system. I think they have the measurements to do it. It is not clear ultimately that is the winning scheme, but it is an alternate approach. It is a very good one that will be tested out. The problem is it also requires you to build. The error correction there is a little more difficult. So again, if you want to do the general purpose problem, again, then you run into how you keep adding on to the entanglement piece. And building an initial entanglement bundle is hard, but doable. But it's the addition that gets to be the hard part of the problem. So it seems like you traded off one thing for another, which wins?
Which means that you have to try both, I suppose.
Yeah.
Thank you.
If you have a lattice or a cellular automata, any of these, regardless of the technology, either experimentally or in simulation, what do you do? What about boundary conditions? What happens at the edges?
So the ends don't actually have to have them. In fact, it actually helps because it allows you to do the initial setting of the conditions on the cellular automata. So you don't need to have ends. There are special conditions and rules if you go back in and look at the paper. You can look at what happens if you have periodic boundary conditions as well, and it will work either way. There's just slightly different constraints.
Like a torus.
That's right.
A cylinder.
Or a cylinder, or I set I pre-entangle the ends so I can actually tell where the stuff across them. So I effectively wrap it through using entanglement at my chains. I mean, so there are a couple of approaches to that idea, and I think most of them are talked about in that paper by Gavin Brennan and Jamie Williams.